So I'm not very good at this introducing people, but I think that this time around it's kind of an odd introduction because hey,
His turn.
I'm talking. So Andrew is actually part of the original first batch of Kavli fellows, if I'm correct. And we're lucky to have him back today. Before he was a fellow here, Andrew collected a long experience in dark matter researches. He started as a grad student in UC Santa Barbara, working in the early days of CDMS, and then later on moved on to neutrino physics. He actually managed the installation of the Orexino detector in Gran Sasso. Then he was with us, and ever since when he was here, he started this search for bubble chambers that we called COO originally, and now we call it PICO. And ever since, he's been working in this area. Now he's expanding into action searches. And after the Kavli Institute, he was a Wilson Fellow at Fermilab, and now he's a senior scientist there. So let's welcome him.
Thank you. It's great to be here. This building is amazing. I wish you had this. So. The old one kind of looks like an elementary school now, the cinder blocks. Okay, so I thought, if I'm going to give a talk at KICP, usually I start with, galaxy rotation curves and the Foley cluster, but that seems ridiculous. So I thought, well, probably they haven't heard very much about bubble chambers. So I'll start with a little bit of a recollection of the age of bubble chambers. So it all started with Donald Glaser, who is here. He discovered bubble chambers, which actually are very much like the ones we build now, more like the ones we build now than the ones that came later. And Glaser built this little glass bulb filled with ether when he was a instructor. He was really very young. And he pretty soon, he did actually a systematic study of ways to look for, in a visual way, to look for interactions for the purpose of studying cosmic rays. He was really a cosmic ray physicist working with cloud chambers, and he wasn't getting enough interactions on vapor. So he wanted to put in a liquid and see if he could boost the rate. Because at that point, he was the cosmic ray physics was being overtaken by accelerator-driven physics. So he discovered that he tried several things, but then discovered that he could get bubble tracks in a liquid. And he had a theory of how to do that I will mention later. But then, a really interesting thing happened. He met Luis Alvarez at the first meeting where he tried to present his results, at an APS meeting in Washington. He went and he sat down, he didn't know anyone. Luis Alvarez was sitting with his wartime Manhattan Project buddies and sat down next to him and said, "What are you working on?" "Well, I'm working on this, this thing I call a bubble chamber." And Alvarez got really fired up and immediately went back to his hotel room and started thinking about how to scale bubble chambers up so that you could use them in accelerator experiments. And it turned out that they never did anything in cosmic rays because they can't be triggered like Geiger counters, but they were just what the accelerator people needed at that time. So ironically, then, the accelerator people started to run with it. And Glaser, because he was really kind of a small experiment person, he did do some more things in this field, but he was really kind of more of a small experiment guy. He was a little bit decoupled from it later on, apparently. But Alvarez, of course, had invented 3 different kinds of radar in World War II and had no problem getting funding. He went to Washington with his boss, Ernest Lawrence, and came back after an hour presentation with $2 million or something, which was approximately 1,000 times more money than Glaser had to develop this bubble chamber in the basement. And so this is a great quote. If anyone had an idea, you could just start working on it right away. He didn't write proposals, and so after 7 years, this is what he had, which these days you wouldn't even get past CD2, I guess. So that was pretty amazing. And of course, the legacy of this is all these beautiful images of particles being created and destroyed and orbiting in magnetic fields, which if you talk to someone who's not a physicist, or not a particle physicist, they might think this is, but knows a little bit about physics, they might think this is still what we do. But of course, we don't do that anymore. And it's interesting to consider why we don't do it. So this is another figure from Alvarez's Nobel Prize lecture showing the number of events they could analyze in their bubble chamber per year in the Berkeley program versus years from 1955 projecting out to the end of the 60s. And so he started with, I guess, 24 a day, so 1 an hour, maybe up to 2 an hour. And he was amazed that by the end of this, they were getting up towards analyzing 1 million events a year. And he's very proud of all the computing machines and scanning machines they invented to ramp the rate up. But for comparison, LHC beam crossing rates are every 25 nanoseconds, I believe. So that's 40 megahertz with something on the order of 10 interactions per crossing. And you might say it's not fair to compare because, of course, the trigger systems select a much smaller number of events to analyze. But in a bubble chamber, there is no way to trigger and analyze only a subset of events. You just get everything. And by the way, bubbles grow rather slowly. So in some sense, 1 second of the LHC, you collected more, there was more stuff produced than was analyzed in the whole history of bubble chamber experiments. And so nowadays, the main application of bubble chambers is just as Lorne ornaments at national labs. They all have them, including the CERN, the Gargamel chamber that discovered neutral currents at CERN. That's the most interesting one to look at. But we have the big 15-foot bubble chamber at Fermilab. And these are made of durable materials, unlike current detectors, and so they will last out in the Chicagoland weather for a long time.
That's Fred Cowie up there?
I think that's Fred Cobley getting a tour of the, probably groundbreaking for the KICP at SLAC.
It's a 70mm movie camera on top.
Oh, it is? Okay.
Of the Fermilab.
So that was, bubble chambers came to an end in the 1980s. But, what else was going on in the 1980s? In the 1980s, there were the first dark matter direct detection experiments after a paper by Goodman and Whiddon in 1985. And what I'll argue is that the bubble chamber people who were getting out of the business should have thought about that and immediately dived into bubble chambers for studying dark matter because they, already everything they needed to know was known at that time. But the basic, the people who jumped on the Goodman and Whiddon scheme were working on semiconductor detectors to study double beta decay at underground sites. And so what Goodman and Whiddon pointed out was that the cross-sections and kinematics were such that if you had a weakly interacting massive particle trapped in the galactic halo with a typical speed of a couple hundred kilometers a second, because it had to be less than the galactic escape velocity, in a mass like the weak scale, 100 JeV, and it scattered off of atoms, off of nuclei. Thankfully, we have nuclei that have about the same mass, so you get an efficient transfer of the kinetic energy, which turns out to be about 10 keV. And in the semiconductor, you produce up to 1,000 electron hole pairs, then you drift them and you get a signal. So that was the scheme that people started working on. It was easy to calculate the expected signal. If you had a beam of these dark matter particles, it would just, this is low energy, non-relativistic isotropic scattering. It would produce a kind of box-like spectrum from the beam with a maximum energy. It depends on the WIMP mass and the nucleon mass. And then this just has to be convolved with the expected velocity distribution for dark matter trapped in the galactic halo. You can do something complicated. This has been simulated. You can try perturbing this, but what people do in the field is assume that it's a Maxwellian distribution with an escape velocity cutoff. And you get energy spectra for deposition in a detector that look like this, with the heavier dark matter particles producing events at the high energy, and the lighter ones piling up at lower energy. For a given cross-section, the number of events you expect decreases with mass, because to get the number of flux of particles, you take the known amount of dark matter and divide by the particle mass. And then you make a exclusion plot the result of all these searches, since there haven't really been detections, real detections, I think, is an exclusion plot. And this shows how from early data they were made. You take a background which has unknown components in it. So you have to assume that the thing that's measured, which are the blue dashes here, that's real, somewhere in there there's a signal. And so you fit the lines which just raise that, and you make the envelope. At low energy, you can't detect light WIMPs because all the events piled up below the detector threshold, and at high mass, the events are going away because there are not enough particles. So what nuclei do you want to use to do this search? There's an important experimental distinction between spin-dependent couplings and spin-independent couplings. Spin-dependent couplings are simply those where if you flip the spin of one of the particles, the scattering amplitude gets a sign change. In spin-independent couplings, there's no sign change. And at low, for non-relativistic scattering, everything breaks down into one of those two categories. Since the nucleons in the nucleus are in opposite spin pairs, and the interaction is coherent over the nucleus due to this large de Broglie wavelength of the incoming dark matter particle, you get cancellation in the case where there's a sign change, and so the coupling is just to the total spin of the nucleus times the form factor. And in the spin-independent case, you get a coherence factor of atomic number squared, which boosts your sensitivity by about a factor of 1,000. So that's actually what people focus on in the early days, is to try to take the maximum advantage from the coherence factor to probe the smallest possible cross-sections. But of course, there are cases, this is very model dependent, so there are cases where you could have spin-dependent couplings that are so much larger than the spin-independent that you have to look for both. Ultimately, we'd like to build experiments, and this is very important to the bubble chambers, that have a variety of different spins and different atomic mass, so that you can probe the scaling of cross-section of these things. So the problem with all the early experiments, what I call the first generation experiments, which were just counting experiments, was the background from environmental radioactivity. So this shows a paper that may have had Juan Collar on it by Ron Brzezinski et al. From one of the early groups, showing how they worked by taking a typical low radioactivity detector in a cryostat. Eventually they moved underground and they substituted one material for another, always pushing towards lower backgrounds, always trying to replace more radioactive things with less radioactive things, and eventually getting down to a lower level. This became really hard work after a while, especially because the parts of the detector which you built above ground were exposed to cosmic rays, at least for some time, and so there inevitably are isotopes that are produced in your machine shop, and it just becomes really hard, after you've made a certain amount of progress, it becomes really hard to go further down. So that characterized the first generation of experiments. What I think of as the second generation of experiments incorporated some kind of discrimination mechanism to tell the difference between the nuclear interactions of a dark matter particle and the backgrounds, which were primarily from Compton scattering or photoelectric scattering from things that emitted betas or gamma rays. And there are over time there have become quite a large number of schemes for doing this kind of background discrimination. Here's just a list of them, because I won't talk about any except the ones that are relevant for bubble chambers. So you could look at pulse shape discrimination, differences in pulse shape in scintillation light in noble liquids or maybe in solid crystals. That technique is used by something called DarkSide, liquid argon experiment, DEEP, another one, and some solid crystal sodium iodide experiments. Or you could look at the ratio of ionization to scintillation produced in a noble gas. This has become the dominant technique now, being used by the liquid xenon chambers like LZ and Lux. And xenon, this is an experiment called Xenon at Gran Sasso. So that's now the dominant technique. You could also look at ratio of ionization or scintillation to the total thermal energy that's deposited by the interaction. In a cryogenic detector, that's what CDMS does. You could look at annual modulation due to the motion of the Earth around the sun as the sun is moving through the galaxy, etc. But what I'm going to talk about then is using the physics of bubble formation to do the same discrimination. And For every technique, there's now a group of people actively developing that technique, and that's why people sometimes look at these plots of all the experimental activity and wondering why there's so many competing groups. Well, everyone is working on a different discrimination technique. This is from the SNOMAS 2013 meeting, and it shows in solid lines the groups that had published at that time, and in dashed lines the groups that hadn't yet published. These are projections. Some of the projections later, since then, the last 2 years, became real. So the Lux line came in right where it was supposed to be, more or less. I believe the dark side is almost where it was supposed to be. So there's actually been almost an order of magnitude, I think, in the last couple of years since NOMAS. And we keep on just marching down. These are somebody's favorite supersymmetry models down here. And down here, eventually, by the way, in another decade or so, we're going to reach a background that can't be reduced, which is from atmospheric and solar neutrinos scattering in the detector on nuclei. So that looks exactly like the signal. And at that point, we're going to have to think really hard about whether we want to continue building detectors where we'll have to somehow just count in excess of this irreducible neutrino background. So if you wanted to build the perfect dark matter detector, what would you want to do? Well, you would want to have a large target mass, obviously, have more events. You would want to have a low energy threshold for what we call standard WIMPs, maybe 30 JeV in mass and above. You want the energy around 10 keV. Nowadays, there's a tendency for people to want to go to even lower thresholds. And you'd like to explore multiple target nuclei in order to look at the A squared and spin effects that I mentioned previously. Of course, all this has to be done without any background for environmental radioactivity. As a bonus, you'd like to measure each nuclear recoil energy so that you could look at the energy spectrum, which is one of the predictions of the model. And the holy grail of the field, perhaps never attainable, is to measure the recoil direction, because as the Earth spins and the galaxy and the solar system moves to the galaxy, that direction will change during the day, on average. That's very hard. We probably had talks about that here. And what could bubble chambers do for you? Well, here's the checklist. We already knew bubble chambers could get very big, like Gargamel or the Fermilab 15-foot bubble chamber. What most people did not know about bubble chambers, but at least the early bubble chamber physicists knew, is that the threshold for production of an individual bubble is actually very low energy. That's kind of strange when you think about these things looking at multi-GeV tracks, but really, as I'll explain in a minute, the energy for one bubble is very low. But I think where we would really make the biggest contribution is in this area of having multiple target nuclei. Glaser at one point claimed that every liquid that had ever been tried in a bubble chamber actually worked. I think with the exception of water, which later was shown to work, but just not very well because of the large surface tension. So essentially, if you had a successful design for building bubble chambers, you could put a lot of different elements into the chamber, and you could really study the scaling of these interactions. So that would be attractive. Then there's the question of backgrounds from environmental radioactivity. Well, that's still to be determined. We made a lot of progress. This is the big question, can we do that? You can't measure nuclear recoil energy with bubble chambers. There's no information there from the observation of the bubble. Okay, so before I talk about the energy threshold and background discrimination, I should tell you about how bubble chambers work at a very basic level. Of course, the way it works is you start with a liquid, and then you rapidly decrease the pressure. That in bubble chamber lingo, that's called expansion. That's the expansion cycle. You cross over the phase boundary into the region where there's supposed to be a gas, and it's superheated. So why don't you have a gas when you cross over into the superheated region of the diagram? It's because in order for a liquid to turn into a gas, first you need to produce a bubble. A bubble has a surface tension, so there's an energy cost to produce a bubble. And it was shown by Seitz in his model for how bubble chambers worked in the late 50s. This is actually not how Glaser thought they worked, by the way. It was shown that there's a critical bubble radius if bubble, this is the surface tension, the radius is the surface tension divided by the vapor pressure of the liquid minus the actual operating pressure of the bubble chamber. So this, if a bubble is made with larger than this radius, it will expand without limit. If the bubble is smaller than this radius, it will collapse back into nothing, and you'll never observe it. So there's an energy barrier. You have to create a bubble that is equal to the critical radius, which corresponds to a certain amount of energy, which is much greater than kT. Otherwise, the thing will just cook off immediately. And if you've done that, then the bubble will grow to any size you want so that you can measure it. And this energy can be explicitly calculated. It consists simply of a surface energy term. This is the threshold, that's the critical radius. There's a surface energy term, and then there's a latent heat from evaporating the liquid that has to fill up the bubble. And so here's an example for one of the liquids that we use, CF3I. We like, by the way, fluorine because it's a great spin target, and iodine because it's very heavy, so it's a great spin-independent target. These are some of the calculated bubble nucleation energies as a function of temperature and pressure, which obviously are things that we, the bubble chamber operators, control. So, for example, if you operate at 35 degrees, which is typical at maybe 30 psi, then the energy threshold is around 10 kiloelectron volts. You could go even lower, you could go down to 2 keV, or if you wanted, you could go up to a higher energy threshold. So this energy threshold can be both very small, it can be large, and it can be very easily tuned by the designer. Not only do you have to deposit a certain amount of energy, you have to deposit that energy inside the liquid that will eventually become the bubble. So there's a track energy density requirement as part of the threshold. There are really two thresholds. There's a total energy and a track energy density, or DEDX. And so in this plot, we show how those two thresholds combine. If you have a recoil of a nucleus, for example, of carbon, it has a DEDX which changes according to its energy, going from about an MeV per micron down to a couple of tenths of keV per micron. And so by tuning the pressure and temperature, you choose a quadrant on this plot, and you can become selectively sensitive to different types of particles. In order to see electrons, which have a very low DEDX, you have to go to either very low pressures or very high temperatures. And this is the basis of discrimination between backgrounds and signal. Your signal lives in this region, it's recoils of heavy nuclei, and the backgrounds are scattering on electrons, which are down here. This physics was known very well, even in the classical bubble chamber era, although it was not used. So, for example, here is a paper from IEEE Transactions on Nuclear Science, somewhat obscure for this field, in 1969, showing this little propane bubble chamber that was made, actually to do something crazy, which was to study carbon-14 content of organic samples. So that application never worked. It was it's a weird one to think about, but anyway, they published this data on discrimination between different types of particles in the bubble chamber. So they started with this difference between the vapor pressure and the operating pressure, which is what appears in the equation for the critical radius of the bubble. So you start at a low value, and you see only the most heavily ionizing particles. Then you increase that, you see more lightly ionizing particles, protons, and then you increase some more, and eventually the electrons turn on. So if you wanted to look for dark matter in this bubble chamber, you would operate down here where you're seeing proton recoils. In this case, the liquid was propane, so the nucleus was hydrogen. And so it's the nuclear recoils are proton recoils. So you could operate here and look for proton recoils from dark matter and be totally insensitive to the electron recoils up here. Exactly how insensitive is something that we now measure very well. So we build small bubble chambers and expose them to intense radioactive sources. And here are results for the two liquids that we currently use, C3F8 and CF3I. And you'll see that For example, at low thresholds, in C3F8 as low as, let's say, 3 kV, we have a probability per gamma ray interaction in a liquid of 10 to the minus 9. That's extraordinarily low. It's much lower than any of the other background technologies afford. For example, the corresponding number in cryogenic detectors is probably 10 to the minus 6. In liquid xenon, it's about 10 to the minus 2. So this is an extraordinarily high degree of background separation power. And what it means actually is that we can build our detectors with very relaxed radio purity requirements compared to what you would need to do any of the other technologies. So this, going back in history, I rarely show this slide anymore, but this is the first bubble chamber that we made in the Wands basement lab in Laser in 2003. It consisted of a little test tube full of CF3BR. We were thinking about bromine as a target at that time. And this looks a little bit like Laser's original bubble chamber. It was partly inspired by it, actually. And so then we have, the main addition is that we have electronic cameras now, so we can take video. And we took videos of bubbles expanding, including one which I think is here. So, yeah, so here's a video. This is 1,000 frames a second, so each frame is a millisecond, and you can see the bubbles keep just getting bigger and bigger. Sometimes people ask, how can you see one bubble in a bubble chamber? There are usually millions of them. But as this illustrates, the bubbles just keep on growing until you tell them to stop. So it just keeps going and going and going, and eventually there's a big explosion, or there's some kind of complicated mixing phenomenon. So that was an early result. We discovered, as Laser did, that you have to keep these test tubes really clean. Otherwise, when you expand the liquid, you get bubbling on the surface. But if you manage to keep it clean, then nothing happens when you expand. You can wait for a long time, and eventually pop, a bubble will appear. And you can make those bubbles appear with radioactive sources, with neutrons if you want to do calibrations. So this issue of clean versus dirty chambers goes back to the very early days of bubble chamber design, and it really is critical for what we want to do. Originally, Glaser built these clean glass chambers, and he really insisted on getting everything as clean as possible. And Alvarez came in and said, well, what I want to do is just build a big vat of liquid in a steel container. And yeah, the walls are going to start bubbling, but I don't care because I have a particle beam. I'm going to spill the beam into the detector at exactly the same time as I expand. And we'll take some photographs before the bubbles from the wall grow in and disrupt the whole volume. And so that's the way in which conventional bubble chambers always worked after Glaser's initial experiments. This is a diagram of how it's a 1 meter hydrogen chamber at SLAC worked. The operators would they had huge pistons, and they would rapidly swing the pressure down. Bubbles from the walls would immediately start growing on the time scale of milliseconds, and then they would slam the pressure back up right away. And so then they would wait for usually around a second before repeating the process. So the actual sensitive period was only 10 milliseconds out of the second. So obviously you can't, if you don't know when your dark matter is going to arrive, this kind of bubble chamber doesn't work at all. So in order to do what we wanted to do, we had to go back to these very clean chambers. And this is a typical cycle for one of our chambers now. We slowly relax the pressure. It takes 3 seconds here. Then we wait for up to an hour with nothing happening, just superheated liquid. And then eventually, we're always monitoring this with electronic cameras, and a bubble appears, and then we raise the pressure, and then we start over again. So we can be sensitive to dark matter particles arriving for more than 90% of the operating cycle. Of course, there's a problem of scaling this up. You have to, it's a lot different to have a small little glass vial and to have a big glass container. There are serious engineering issues with large glass things that are under pressure. And the way we solve that problem is by having a 2-fluid system. So we have, well, there are actually 4 fluids on this drawing, to be fair. So we have our target liquid in a very clean glass, actually eventually fused silica synthetic glass container. The target liquid has water or some other inert liquid that's not going to boil floating on top of it. And the water is in contact with the metal bellows that can flex. this whole thing is surrounded by a second volume of liquid, where the pressure equilibrium between the two things is maintained by that bellows moving. And so there's never any pressure to speak of across the glass. All the pressure is held by an external steel pressure-containing vessel. So this is a way to cheat and to make a glass vessel that doesn't have any, it can be big, but it has no stress on the walls. And you can scale this up as large as you want, at least as large as someone will provide a glass vessel for you, which with very high purity glass did turn out to be an issue. So that's what we do. This is a more complete drawing of what our chambers currently look like. This is a small one, but you can see here's the pressure balancing bellows. Here's the fused silica glass vessel with target liquid. We have stereo view with cameras looking at the volume. And all this is contained in basically a standard industrial steel vessel with moderate concern paid to selecting low radioactivity steel. And that's, of course, what the thing really looks like. And we've also paid attention to getting good photography. This is actually one of the things they had to do to get those beautiful images that you saw is work a lot on pictures and on optics and illumination. So we had actually probably 5 years of iteration to rediscover the secrets of bubble chamber illumination. But eventually we got these beautiful pictures. This is an event from multiple neutron scattering. So a neutron came in, scattered 3 times, and produced 3 bubbles. One of the very nice features of a bubble chamber where you have a homogeneous volume is that if you have neutrons rattling around, you can spatially resolve all the vertices. So since neutrons are a background issue, you can know whether they're there or not by how many bubbles you count. And then this is the larger chamber that we built at Fermilab. There's the steel pressure vessel and the inner vessel, which was built in Japan by the one supplier in the semiconductor industry that could handle such large pieces of fused silica. And you can see we did pay a lot of attention to making it as clean as possible. And that's the full system being tested at Fermilab. The bubble chamber is inside this black plastic water tank, and the pressure control apparatus is all outside. We don't need one of those big pistons that you see in the old-fashioned chambers because we are just raising the pressure very slowly compared to what they had to do. So that simplifies the situation a bit. Okay, so I talked about gamma rays. We have almost negligible sensitivity to gamma rays and betas. What about alpha particles? So in this quadrant of the threshold diagram where the signal appears from iodine and carbon, well, not carbon and fluorine recoils, that's the signal, nuclear recoil. There are also alpha particles from radon, which is a very common isotope that is around in the environment. And besides the alpha particles themselves, when a nucleus emits an alpha particle, it recoils with about 100 keV in energy. So there is no dark matter, there is no where you can set the bubble chamber where you will see a 10 keV iodine recoil, and you will not also see a 100 keV recoil from the daughter of radon. So that is a problem. We have to get rid of those alpha events. And this is a very complicated slide, but it shows the results from our 2006 run at Fermilab, where we were plagued by this alpha background. The alpha background has a different shape in energy than a WIMP would have. So you can map that out by scanning the pressure, and you in that way spectrally discriminate between alphas and gamma rays, but it's really a mess. So at that point we thought, well, we really just have to by brute force reduce the level of alpha contamination in the liquids, as solar neutrino experiments do, for example, by distilling the liquids and bringing them up to very high purity. But we thought this would be a persistent problem. Now, there's one way you can imagine getting around the alpha problem, which is, suppose you had a very high resolution microscope. So this is an optical device that I think cannot exist in reality. But imagine you had a microscope that was able to resolve micron-sized things, which you can do, of course, with a microscope. But you have to resolve it over the full volume of the bubble chamber, and you have to resolve it with the time resolution of microseconds. in order to see this effect. But if you had that miracle camera, then what you would see when you looked carefully at the alpha events is you would see a chain of bubbles from the alpha. An alpha track has a length in liquid about 40 microns. So you'd see bang, 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 bang. And if you looked at a nuclear recoil, the nuclear recoil is much more contained in 100 nanometer or so volume. You would see just one bubble. So it'd be really nice to have that camera. Unfortunately, we don't have that camera. But it turns out that there's another effect which seems to measure the same thing acoustically. So imagine that all of those bubbles are radiating sound, and they radiate sound in the first few microseconds of the bubble nucleation. Then this signal from many bubbles will add up to a larger amount of sound than that signal from a single bubble. There was a competing group working with another kind of superheated liquid detector called superheated droplet detectors based on dosimeters. And this is the Picasso group that worked on this for many years in Canada. And they, in 2008, discovered that the neutrons made, nuclear recoils induced by neutrons made softer sounds than the bubbles produced by alpha particles. So they started to see this effect in their chambers. We then repeated this with a bubble chamber, and lo and behold, it turned out that it worked much better in bubble chambers than in these dispersions of superheated liquid droplets where the sound had to propagate through many liquid interfaces. So we got a very clean signal. We found that there was apparently almost complete separation between a population of nuclear recoils and a population of alphas based on this acoustic signal. Alphas, depending on the analysis, alphas produce 4 or 5 times more acoustic power than the nuclear recoils. So at this point, I would say we really thought we had it made. It looked like we had almost complete separation between alphas and nuclear recoils, and that was the only background that was evident. And so, actually, it was so convincing that the people who formerly worked on Picasso, the competing group, decided to join us and just work on bubble chambers. And so in the process of this, we picked up a large number of collaborating institutions in Canada. This is the current collaboration with a group that is more or less half US, half Canadian, with a couple of other institutions scattered around the world. And we, of course, do the research now at Snow Lab, which is 6,800 feet underground in Ontario. They built a beautiful facility which now has something like half of all the world's dark matter experiments in it. You can see here, this is the site of the old Sudbury Neutrino Observatory, and this beautiful facility has been built off on the side with room for a liquid argon experiment called DEEP, and this is actually future expansion for another big detector, plus some small experiment space. We're located in one of these side tunnels over here. And there are some
Where does
recent,
CDMS go?
CDMS will go next. CDMS is relatively small. They'll go actually right next to the bubble chamber. And here are some recent KICP alumni who you might recognize installing the small chamber. There's Alan Robinson and Eric Dahl installing the small chamber underground at SOA. And there's the big chamber being installed. Well, it's just a pretty picture. You can see we're picking it up with the crane. That's the slice of the inner vessel, and that's the water tank that we have underground there. So what did the results look like? Well, we ran the big detector in 2013 and 2014. We had 37 kilograms of CF3 eye, which again, because of the iodine, has good sensitivity to spin-independent interactions, and the fluorine spin-dependent interactions. Technically, the detector worked wonderfully. The lifetime fraction of the time when the liquid was superheated was more than 90%. And we accumulated 5,000 kilogram days of exposure, which was, at the time, and still is one of the largest exposures of any dark matter detector. And this was at several different energy thresholds, down to 7 kV. And so what did we see? Well, we saw a lot of events. We saw a lot of bubbles, actually a fluctuating rate that was between 10 and roughly 100 counts a day. And it depended on all kinds of things, including what was the operating temperature of the detector. If we had temperature instabilities, for example, here we show this is the temperature which is oscillating due to an instability in the temperature controller that controlled the temperature of the water bath. And every time the temperature jumped up, the rate went through the roof, which is something that should not happen for WIMP dark matter. Also, you'll notice that these bubbles occurred very non-uniformly in the chamber, so this is not dark matter. Furthermore, the acoustic amplitudes are not those expected for nuclear recoils, nor are they those expected for alpha recoils. So the blue is a source of calibration events from neutrons, and the red is this background that we're seeing. There's about 20% excess acoustic power in this new background. And there's a close-up of the signal peak in blue. And so it shows that there's starting to be decent separation, but unfortunately these are partially overlapping distributions. Well, we took the source of it. So we have these are different runs. We put neutrons into the chamber, we see nuclear recoils. That's calibration. We take the source away, we just collect data on dark matter passing through the detector, we see events. Those are the background. There are other interesting characteristics. One of them is that the longer the chamber is expanded, the lower the rate of the background events are. Whereas other things behave as you would expect. This is the rate of alpha decays in the chamber, which is more or less constant with the expansion time. And the rate of these background events is decreasing with expansion time. That means the longer you wait before a bubble occurs, the longer it's going to likely to be before the next bubble. So we looked at the spatial pattern of events and thought, gee, this is very reminiscent of what you might expect from convection currents in the liquid. We already knew that the impurities in the liquid, dust, in chambers that were more contaminated, tend to accumulate at the interface between the target liquid and the buffer liquid which floats above. This is much like the kind of soap scum that you see in your bathtub. The interfaces become contaminated with particulates, if there are particulates there. So it looked as if maybe convection currents were sweeping something down into the bulk from the surface. And so we decided to go take the sector apart and look for any scum that could be there. Was there some kind of foreign material floating around in there? And when we did that, we passed the liquids through some very fine filters. And yes, we discovered crud on the filters, which with some pretty interesting techniques we borrowed from material scientists at PNNL in the University of Alberta, we were able to determine what all these things were. It turned out there were basically two classes of things. There were chips of quartz, presumably from the quartz vessel that the liquid is in. And then there were chips of stainless steel and iron oxide, which presumably are from the steel bellows structure that is used for pressure control. So as you might expect in retrospect, the bubble chamber sheds its surfaces into the volume at the level of micrograms over the course of operation. So this is just an illustration of the fantastic techniques that are available now for identifying small particles. You take an electron micrograph of this thing, and you wonder, what is that? I have no idea by looking at it. But you can get an X-ray spectrum, and you discover that that's iron oxide. It certainly doesn't look like a particle of rust to me. But it's amazing what you can do now. We have an idea about what the mechanism might be for creating these bubbles. It's a little bit peculiar that the bubbles make a sound which is so close to the sound of a nuclear recoil. If they're really just boiling off of a rough surface, which is a completely different mechanism. So we wonder if maybe this is really due to radioactivity. For example, if you have a alpha-active nucleus embedded in a dust particle, and the alpha particle decays, if the dust particle is small enough, some of the alpha energy and the nuclear recoil can be contained in the dust, and the alpha particle can come squirting out and produce an acoustic signal which is diminished in intensity. And so that's the basic model that we've considered to be the most promising source of these events. But that's not proving it, by the way. Now, given that the events, every way you plot these events, they look different than the signal. If you combine all of the anomalies together, the expansion time anomaly, the fact that they tend to occur higher in the chamber, if you combine all these things together, you can actually set a good limit on the population of dark matter events that could still be there. We essentially draw boxes with no events in them, and then we use Monte Carlo methods to estimate a statistical penalty for having the freedom to draw the box wherever we wanted it to be. The details of that are a little bit complicated, but we'll find them in our paper, which is on the archive, if you're interested. So we do that, and we actually get a very nice result. This is the sensitivity of that run from Pico 60, and this is the current best sensitivity of CDMS and the sensitivity of the dark side liquid argon experiment. These are for spin-independent cross-sections. Now, for liquid xenon, we are now an order of magnitude or more behind. Another story, bubble chambers have been very successful over the last decade. Liquid xenon chambers have also been very successful. So now we regard this sort of as a race. We've caught up to the alternative technologies. The xenon guys for spin-independent are winning. On the spin-dependent side, things are a little bit different, as I'll explain in a second. But first, let me show you the data from the small chamber. At the same time as we ran the big chamber, we also ran the small bubble chamber called Pico 2L, which with a lower energy threshold than with C3F8 instead of CF3I. So we have more fluorine atoms in there, which are the ones for the spin-dependent sensitivity. And we run at a lower threshold. We also saw an anomalous background component, very similar in nature to what we saw in the big detector. But there were fewer of these events in the small detector for whatever reason. There were only 9 at this threshold in 32 live days. And that was 2013, 2014. More recently, and this went on the archive just last week, I think. So more recently, we released the results from our 2015 run with a very similar exposure. We made 2 changes really. We cleaned the detector much better, and we replaced the high purity quartz inner vessel with an even higher purity grade of quartz, because we suspected that maybe this is an effect of the radioactivity of the quartz. And lo and behold, we have just one event in this data set, similar, or actually twice the size of the previous data set. And that one event is consistent with our estimates of what the neutron background at that site should be. So we've really, looks like we may have succeeded in eliminating the backgrounds from this dust by being more careful about assembly. And this shows our spin-dependent cross-section limits. The small detector, the 2013-14 run is in red, and the more recent result is in green. And then the large detector with CF3I is in blue. And so this shows that for the spin-dependent cross-sections on protons, we have the world's best sensitivity, actually by a pretty big factor right now, with the large detector with the higher threshold coming in at high wind mass, and the small detector at low wind mass. Also, because of the low threshold, we also have some interesting sensitivity for spin-independent cross-sections at low mass, where we're now quite competitive actually with CDMS light and with super CDMS. So we're if you really believed exactly where these curves are, then you would say, oh, you're behind everybody else. But in fact, there are real uncertainties here to the calibrations at low energy threshold. And so I think this is a very valuable contribution to the field. Commonly is a little bit lower than everyone else.
The uncertainties for CDMS, right?
Yes, right. Uncertain is in other guys, not our uncertainty. we know exactly what that line is.
Well,
and
and
so,
super CDMS has not happened, right?
yeah, I think that's mislabeled. It's really CDMS 2, but it's the Sudan. It's the Sudan. It's the
They call
Sudan.
it super CDMS. They do call it
It's the
super CDMS
Sudan
and
case.
Sudan.
Oh, okay.
And this is my last slide, by the way. So what are we going to do now? We're preparing for another run of the large bubble chamber, having made improvements to cleanliness. The main thing that we've done is installed a system for continuously purifying the liquids during the run, so that we're going to be either continuously or episodically filtering all the liquids in the inner vessel, removing particulates, and then running. If this succeeds in getting rid of the background events that we've seen, there's potential for 2 orders of magnitude better sensitivity than that existing hardware. For the longer term future, we are unhappy with one design element of this bubble chamber, which is the water target liquid interface where the kind of bath scum tends to accumulate. That's an undesirable feature of the detector. It would be nice to have a detector that did not have that interface, which is a potential place to store up particles where you can't easily recirculate them through a filter. So we're kind of redesigning the chambers to get rid of that interface. In the future, we hope that will be done with a controlled thermal gradient in a target liquid such that you have a non-superheated liquid at the bottom just because it's cold, and then the top will become superheated. And that actually, in the history of bubble chambers, that was already tried, and it does work at least at some level. So thank you. That's the talk. And I wanted to say Juan is looking for graduate students. If there are any in the, that's the main thing we need besides another bubble chambers. We need more students. It's a great opportunity.
You hear that, the grad students. Before we go into, do you have any projections? Do you have the slide with the projections for, talk about 2 orders of magnitude?
Well, no, I'm sorry. I was too shy to include the 2 orders of magnitude
Things
projections.
are looking really good now that we seem to have solved this problem with the dust scam problem. So who has questions?
What did you do to solve the temperature dependence in the counts?
Well, so we've installed a better temperature regulation system. It's a better temperature regulation. We should get rid of the temperature oscillations. But if those are due to the particles floating in the liquid, then when we take the particles away, even if the temperature starts to swing, then we shouldn't see that. Steve?
Is it really convection that's bringing them into your volume? That also can be controlled by controller.
Yes, well, it could be. So liquids do slightly change their temperature when compressed and expanded. And the target liquid is squishy compared to the liquid that's outside the quartz vessel. So as a result, when you cycle in temperature, you develop temperature gradients that are really hard to get rid of. So we've thought about trying to impose a gradient that would stabilize the conduction cells, but it's rather hard to do that.
Is there any point in the early bubble formation where it still retains the directional information? Very early time.
Well, I think there might be, but it would be sort of at nanoseconds or even picoseconds. And so you'd have to find some way to measure the bubble length as early
Yeah,
times.
but you think you might have the information there?
I think so. Again, but it's just very difficult technically to access.
So the responsible detector depends on the pressure, right? If you fix the detector, I guess.
Yes.
So if you build a big detector, effect on the pressure, the bottom might be meaningfully different. It's going to affect a big systematic or
It's not a large effect if you think about the magnitude of the effect. You would then, of course, you measure the position, and so you would in software, you would account for that variation. We actually already do see an effect on the acoustic amplitude is very pressure.
But it might cause a problem with the threshold.
It's a fraction of a K change.
Okay,
The
so
largest
it's
change.
small.
It's about a tenth of that.
So you would just have to take it into account.
So, one last question.
Do you clean it over and over again, or will it maintain its cleanliness over the duration of your next month?
So we're installing, we never have had the capability. In the past, it's always, these chambers have always been operated as closed systems. Nothing goes in or out during the run. But we've now added a capability to continuously clean the liquid while we're running, which, by the way, is what other large low background detectors do, like snow or forks. You know, all these big low radioactivity experiments have continuous purification of the liquids.
We're the only dark matter experiment that has moving parts inside the target volume. So you're gonna get some dandruff falling in, and we have to take measures. And that's where R&D effort is going right now. We have either active filtering in ECO60, or we're, as Andrew said, we are thinking of another design where there will be filtering, but also not an interface. That's probably the final generation chamber.
So, Andrew, one aspect of this bubble chamber is the rejection of photon rejection, or you get this 10 to the minus 9, which is really very good, which relax the requirement for the low background material. So, on the other hand, wouldn't this mean that you could make, much easier way multi-ton experiment?
Much easier way.
Much easier with respect to other experiments.
I think that's the.
So that aspect has not been, for the moment, you are not emphasizing this aspect. But if thinking about the future, isn't that a winning card?
Yeah, that certainly is. So a lot of the difficulty of building these low radioactivity experiments is in selection of materials. You can't just use any kind of steel or any kind of. Half the work is in either producing special materials or finding special materials and characterizing them. So since we can have relatively radioactive things in there, it makes the construction of the detector much easier. In fact, that's how we were able to make this much progress with a small collaboration and a small budget. So you're right. Maybe we should emphasize that more.
There's also the fact that we operate close to temperatures. It's a non-cryogenic experiment. It's
But I
1/10 of the
What
cost.
I mean is thinking about the future. If you improve on that aspect, you have the possibility of being better than other experiments with much less cost, with a little bit of.
You can also
so equal to liter, because to liter you have one event. If you improve on the quality of the neutron shielding, and then that will be a.
Also, the competing experiments also use very precious materials. Liquid xenon is expensive, and there's a limited amount of it available in the world. The liquid argon, which is being used now, as you know, is specially selected from underground sources and is not easy to get. So the ability to construct detectors with easily obtainable materials, that would lend itself to a potentially very large experiment someday.
So,
There you go.
Yeah, so
But
what
that's-
about this
last two questions, go.
project over summer where they use like temperature to decondense the bubble and bring it down and other pressure cycles? Is this like feature in the main game for people?
So this is there's a design for continuously sensitive bubble chambers where there's a temperature inversion where a bubble grows, encounters a colder region, liquefies and falls back down. We're not actively pursuing that now just because the conventional bubble chamber operation seems to be easier to design and is robust. So it did not seem to solve the problem that we're actually, we're not actively doing that.
Last question.
The acoustic parameter, is it basically just amplitude, or is there any sort of shape and dimension?
It's a weighted sum of different frequency bands that's corrected for the position habits, and also for actually for property. So there are a lot of things that go into construction. There's a bit of black magic that goes into building a parameter that is good at discrimination.
But there's frequency information that we're now exploiting, and something he didn't show is that, for instance, we're doing alpha spectroscopy or calorimetry. We can not only separate nuclear recoils from alphas, but also see the energy, the different energies of the alphas listening to what's happening, which is astounding. It's getting pretty esoteric, this acoustic detection, but it's very powerful. Anyway, let's thank Andrew again.